and welcome to the NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 28 and the topic is band diagram of heterostructure. But before we start with the band diagram and understanding of heterostructure, let me explain to you some of the band diagram and current voltage characteristics of even a homojunction based design. So, let me take up first of all see a rectifying contact, and within the rectifying contact let me first draw for you. So, this is the metal, on the left hand side you have a metal and this is the Fermi level of the metal which you see, and this is the conduction band edge which you have EC prime, and this is before joining, and after joining this is what you get as EC and this is what you get as EV, right, and therefore this will be the discontinuity in the Fermi level which will be there, and this discontinuity will be referred to as between EC and EC and EF will be phi n, and this the initial value, this one is my initial Q phi B n, which is the barrier height for electron, and this is equals to Q into delta phi because of the addition of the two carriers coming closer to each other, because you have applied a bias which is equals to VA, and that VA, because of an application of the bias, there is a disturbance in the Fermi level and the variation between the two is given as QV built in minus VA, right, and this is Q times VA. So, if you apply a bias VA, the Fermi level shifts by a factor QVA in energy scale, right, and this is what you get. Now, if you look very carefully here, electrons on the metal side can easily cross over to the semiconductor side and vice versa, and we define the semiconductor to metal carrier density semiconductor to metal to be equals to E times EC prime. EC prime is this to infinity what Vx times dN, where EC prime is the minimum energy for thermionic emission, right. So, what we are applying is thermionic emission. What we are trying to say here is that when the barrier height is much larger than kT, when the barrier height is much larger than kT, we define this to be as thermionic emission, correct, and Vx is the relative velocity. This is the relative velocity of the charge carriers. So, if you multiply that with respect to dN, where dN is the number of charge carriers, you will get the value of this thing. Now, dN can be written as, which is a very standard form of writing, to be equals to GCE multiplied by F Fermi level E, where GCE is basically density of states, DOS, right. This is DOS and this F of E is effectively the Fermi level or the Fermi function dot dE. So, you see it is the multiplication of density of state and Fermi function. So, when you multiply these two together with the respect to dE, where dE is the incremental change in the energy level, you get the total amount of charge carriers available within that density of state function, right. So, since this is a probability, the F of E is a probability function and G of E is the density of state, when you multiply you get the value of dN. Now, typically if you look this is almost like metal semiconductor. So, this interface, so just I am trying to make it together. This is my metal side, right, and I am sending a current from here. This is the metal and this is my N type semiconductor where I have applied a voltage VA on the semiconductor side. So, I have put a negative voltage here and a positive voltage here, that pushes the energy band diagram on the right hand side much below. So, I can write down therefore that J of, so you see there will be current both from metal to semiconductor and semiconductor to metal, and therefore, the total current which you can write down can be written as J S to M plus J M to S. And if you solve this, this comes out to be a function which is almost like which is temperature dependent function exponential minus E times phi B n divided by k t. This is the barrier height multiplied by exponential E V A by k t minus 1. This A is a constant which is given by 4 pi E m n star k t k square divided by h cube. This is a constant value which you get, and therefore, what we can write down is we can write down this whole statement as, once again we can write down this as J equals to J S T exponential E V A divided by k t minus 1, we do it, where J S T is nothing but A star t square exponential minus E phi B n by k t. What I am trying to tell you from all this discussion is that if you look at this particular point here, this one, and if you look here, then you see that this is almost like reverse saturation current which is happening off state, and this is the forward current in a p-n junction diode, remember. So, what I did, I replaced this whole thing by JST quantity known as JST, and then we have this exponentially EVA by KT minus 1 as the effective value of J in this case, right. And therefore, as the value of VA goes on increasing, more and more current will be available to you, because again it is almost behaving like a PN junction, and therefore, you will have a large amount of current which will be flowing through the device, in this case when you are doing a rectifying contact. This is a good way of looking at it. Therefore, I can write down, therefore, with all this discussion I can write down that del of phi B n is equals to phi B 0, the original barrier height, minus del phi. Del phi is the change in the barrier height by application of a bias, then the new barrier height or the change in the barrier height del phi B 0 can be del phi n. Del phi n is when you have n type semiconductor being attached to the metal, the change will be equals to del phi B 0 minus del phi, where del phi is basically the change in the height or barrier potential, right. And that gives you the effective value for all practical purposes in terms of the value here. Now, if you take this del phi B n, or do you take this phi B n value and you try to put this value back into this equation, then what you get from here is you get an expression which is given as, it can be written as J of S t can be written as A star t square, right, exponential the same quantity, it is minus E times phi b 0 divided by k t exponential E del phi by k t, because you see this is minus del phi n. So, minus of minus will be, so this will become minus, this will become plus, and as a result you will get this expression of JST with you. JST is the, this is basically the sort of a reverse saturation current component which you get when you are adding both n type and p type material together. Now, if you take up therefore the reverse saturation current and you try to compare a Schottky barrier with a PN junction diode barrier, it has been found that the Schottky diode barrier has got much lower cut in voltage as compared to the PN junction. Let me plot here ID versus VD. VD is the voltage across the diode, and I take a Schottky diode, and the Schottky diode cut in voltage will be somewhere here, right, whereas if you take a PN junction diode it will be somewhere here, which means that the reverse saturation current is ideally much larger for a PN junction as compared to a Schottky diode, right. The forward current for PN junction is much larger as compared to Schottky, whereas reverse for Schottky is much larger as compared to reverse for PN junction, right. And it gives you a quite an interesting value which you give. So, if you plot reverse bias VR versus the current IR, both are in the log scale, by the way, both are in the log scale, this is VR and IR, then you get something like this expression, you get like this, which means that as for low values of reverse bias, the current is small, remains constant for a long duration of time, and suddenly it goes to a high value. This region is basically your breakdown. This is the breakdown of the device which takes place. This is the electrical breakdown of the device which takes place. We will not discuss in detail that particular instance in this case, right. And let us see, let us take a numerical example to showcase what I was telling about your reverse bias and forward bias Schottky diode. So, the question is something like this, that the question is that you have to calculate the forward bias voltage, right, to induce current density of 10 ampere per centimeter square in a Schottky diode and a p-n junction diode at T equals to 300 Kelvin. Now, for a Schottky diode, I can write down VA to be equals to KT by Q ln of J by JST. This I got it from that previous explanation, you see. If you look at this expression here, from here I can get J by JST plus 1 you can remove, a natural log of that KT by Q will give you the value of your VA, right. So, from here if I do a small manipulation, I get VA to be equals to KT by Q ln of J by JST, and if you put the value of J and JST for all practical purposes, this comes out to be 0.312 volts, right, assuming that the JST value is approximately 5.98 into 10 to the power minus, you can calculate it very easily. Now, this is for Schottky diode. Now, if we take up a p-n junction diode, then also we can write down VA equals to KT by Q ln of J by reverse bias JS, that is comes out to be equals to 0.682, almost double of the first value. And primarily the reason it is double of the first value is of the Schottky diode is that this JS value, reverse saturation current, is orders smaller for p-n junction as compared to that for the Schottky diode, because of which you get a large value of VA in case of p-n junction as compared to that of a Schottky diode. This I am leaving exercise to you also, that if you take a Schottky diode, then this is basically a majority carrier device, which means that the majority carriers are responsible for the flow of the charge carriers in this device, right. Just look into this in this case. However, there is an issue which I have left while discussing any type of device here, and that is basically the switching characteristics. Now, p-n junction, if you take your Schottky diode, actually works at a much higher frequency, because the switching speeds are relatively also higher, and the reason is that you will have minority current carriers to be removed in a p-n junction diode when you switch the voltage in order to have a fully depleted region. That is not true in a case of a Schottky diode, and therefore the switching speeds are much faster in case of Schottky diodes as compared to p-n junction diodes in that case, right. It is relatively much faster to carry forward with it, right. Now, let me come to metal semiconductor contact, right, and it has got, as I discussed with you, low R in both the directions, and if we, I will just quickly refer to this once again. So, when you join the two together, if you join metal and semiconductor, right, ohmic contact, then my Fermi level obviously will remain the same, but the conduction band will go like this, and then EF will be same. So, EFI will be something like this. This is EFI, EF conduction band, and this is my EV. This is Q times phi Bn, the barrier height which you see, and this difference is Q times phi n because of the application of potential. It has very small barrier. Since it is, the barrier is relatively small, there will be easy charging or movement of charge carriers from both the sides of the material, and that is the reason you get this to be as a ohmic contact. However, if you take maybe an ohmic contact and give a positive bias, forward bias, then what happens is the conduction band shows like this, the valence band also comes like this. So, there will be electron flow from semiconductor to metal in case you give a positive bias to the metal side. If you give a positive bias to the metal side, this will go up, and for them it is a natural slope, and therefore, the electrons will be rushing through to the metal side. Just the reverse if it happens, that if we give a positive voltage on the semiconductor side, then it looks something like this, that I have a Fermi level, and then if I give like this, it will come like this, EC and EV. As a result, what will happen is that there will be flow of electrons from metal towards the semiconductor side. So, now the current density will be from semiconductor to metal, the conventional current. In the previous case, it was from metal to semiconductor. Okay. So, this gives you a brief idea about the ideal metal semiconductor contact and other features related to contacts which are not heterojunction in nature. We also come to what is known as a tunneling barrier. Tunneling barriers are the barriers where the conduction band has risen so sharply near the interface that the effective width has actually reduced, and therefore, there can be effective tunneling between conduction band of the metal onto that of the semiconductor. So, that gives you effectively a much smaller tunneling barrier if you work with this region. Let me now come to the heterostructure band ring, because this lecture primarily looked into the homojunction as well as heterojunction understanding. So, let us go one by one and see what the energy band diagrams are. As I discussed with you in our previous lecture, that if you have different band gaps, right, then automatically there will be a discontinuity at the edge or at the interface of the two band gaps, right. And since the two band gaps are basically discontinuous in nature, this is a discontinuity in nature, you will have an edge of the energy level at the band gap, right. So, there are two types of material as we discussed. There is a narrow band gap and there is a wide band gap, right. Narrow band gap is like silicon, stuff like that, and wide band gap can be any other material which has got relatively a larger band gap as compared to silicon. Now, you can also have an abrupt junction, or you can have a graded junction. Let us suppose you take an example like gallium arsenide and you take aluminum gallium arsenide, right, aluminum gallium arsenide, and say X is varying from 0 to 1, right. This varying of X will change the band gap slightly along the side, and as a result there will be a smooth change in the band gap. In that case, you possibly will not get very sharp edged interface between the band gap, and as the X value changes, you will have the band gap change in a very smooth fashion, and this is known as band gap engineering, right. This is known as band gap engineering, right. So, this is the band gap engineering which we refer to. One more thing which before I move forward is that the dopant type, right. Now, if let me use a blank screen to showcase you. So, if I have a heterojunction, right, if I have a heterojunction here, and it is P, NP basically means that this is N type and this is P type, but P type has got wide band gap material and has got a low band gap material. This can be case, or this can be also a case that I have capital N small p. In both the cases, this type of device are known as anisotropic semiconductors. Anisotype semiconductor, where the heterostructure band gaps are different for different material. Whereas, if the doping is same, like for example NN or even PP, then we define this to be as an isotype semiconductor, right. I mean to say the doping is different, we define this to be as anisotype. If the doping is different, we define that to be as anisotype, same isotype, right. And just looking at the nature of the material, we can easily predict whether it is an isotype or anisotype or isotype material. So, there are three types of band gaps available to us. The first is defined as the straddling gap, and this gap is the most widely used, where the low band gap material, the wide band gap material completely overlaps over the low band gap material in terms of energy, which means that EC2 is larger than EC1, right. EC2 is larger than EC1, and EV2 is also larger as compared to EV1. So, this is fully engulfed within this domain, right, and that is there. If you take type 2, which is staggered gap, this is the staggered gap. Staggered gap primarily means that at least EC1 is larger than EC2 and the band gaps are staggered, they are non-overlapping, fully non-overlapping in nature. So, electrons or holes will be spatially separated. The last type is known as the broken band, and the broken band is one in which there is no overlap between the two material in terms of their band gap. So, this is known as a perfectly broken band gap material, right. For all practical purposes, so we will take the idea that this will be the most widely used. The straddling type will be the one which will be most widely used in case of a energy band diagram for our case, right. So, this is what we are looking into in energy band diagram studies. Now, this I have already discussed with you that P and N, when capital P is referred to as a larger band gap, small n or small p refers to a small band gap. If in which dopant species changes, we define that as anisotype, and when the dopant species remains the same, we define that to be as the isotype. So, now let us come to the sort of an energy band diagram of a narrow band gap and a wide band gap material, right. On the left hand side, if you see, which is this one, this is one which is before the contact, right. Before the actual contact of the material has been made, this is the band gap. As you can see, this is basically a germanium and a gallium arsenide. You remember the difference in the lattice constants is just less than even 0.13%. So, this is what I was talking about, that I do a germanium and a lattice constant. I have a vacuum level obviously, and the Fermi level of the germanium is somewhere here, right, and there will be some Fermi level. This is a p type gallium arsenide near the p type material. This is my work function for the germanium, this is the electron affinity, this is the band gap which you see, this is the electron affinity for the p type material, this is your work function on the p type material, band gap. Since and delta EC is basically the band edge discontinuity of the conduction band, delta EC is this much, right, delta EC is this much. If you write down delta EC, it will be given as E times chi n minus chi p. The difference in the electron affinity of n type germanium and p type gallium arsenide. And if you do delta EC plus delta EV, then this will give you EGP minus EGN, right. The difference in the band gap of the delta EG. EGP is the capital, this should be capital P, let me write down as capital P. EGP is the band gap of the p type material which is gallium arsenide, and EGN is the band gap material of this thing. So, if you add the discontinuity between the two, it is nothing but the difference between the values of your conduction band edge and the valence band edge, right, the value of your band gap, and that will be defined as delta EG. Now, quite interestingly, we assume that whenever these two materials comes in close contact with each other, which is the right hand side graph, I will follow what is known as an electron affinity rule, right, which means the electron affinity will remain the same across the board, there will be no change. With that into consideration, when you bring them together, what will happen is, on the gallium arsenide side, if you can see properly, the bands tend to go down near the interface, whereas for an n type semiconductor, which is germanium in this case, the bands tends to go up. And the difference which you see, delta EC, which is the conduction band difference after the merging of the two bands, is again the sum of this plus this will give you the difference between ECP and ECN. So, if you want to find out the difference between ECP and ECN, then it will be nothing but the sum of EVIP B plus delta EC plus E times Vn. However, delta EC, if you remember in our just now discussion, was the difference in the electron affinity between the chi n and chi p, and this value does not change over a period of time. And if you see here, since it is in thermal equilibrium, the Fermi level is exactly the same across the two boards, and the difference delta EV here is the difference in the value of your energy level, and therefore you see a sudden discontinuity at this particular point. This is what I was referring to, right. And I hope you understand why the discontinuity is larger on the conduction band side and on the lower on the valence band side. Now, this is an example of a 2D electron gas, right, and this is an example of a NN means this on the left hand side is my N type gallium arsenide, on the right hand side I have a capital N type aluminum gallium arsenide of a wider band gap. Try to bring them closer to each other. There seems to be a obviously there will be a discontinuity, and a discontinuity is in this manner, right. So, aluminum gallium arsenide can be moderately to heavily doped to N type. Gallium arsenide is more lightly doped or even intrinsic in nature. So, you see when you join the two together, EFN actually aligns with respect to each other, right, because it is some thermal equilibrium condition which you get, and delta EC is the change in the conduction band edge between the 2 type material, and delta EV is again the change in the valence 2 band material, and the difference between them is the band gap which you see in this case. Band gap is typically equals to EGN which you see. This 2-dimensional electron gas, I will explain to you how the formation takes place. Now, therefore, to achieve thermal equilibrium, right, the electrons from wide band gap material which is on the right hand side, this side will actually move towards the gallium arsenide, and therefore, there will be an accumulation of electron in the potential well adjacent to the interface. So, you see this is the potential well I was talking about. There will be accumulation of large number of charge carriers here, and this gives rise to what is known as a 2-dimensional gas here, right. Now, since the distance is very small, there will be quantization of level, and when there is a quantization of level, electrons will occupy only those quantized energy levels, right. If you are doing a 2-dimensional electron gas, they will be only occupying those quantized energy level, but they are free to move in other two spatial direction. Now, so basically let me go back to this picture again. So, along this it is quantized along this direction. It is quantized along this direction, but it is free to move through the board, right, through your laptop screen. If you look in that manner, in that direction it is free to move if you apply bias, but it is quantized in this. There are specific energy levels here, right, and the specific energy levels have electrons available within themselves, correct, and these energy levels are very much distinguished, and they can be distinguished with easily. Now, the potential function near the interface generally is approximated by a triangular potential well. So, typically those who have studied basic 101 engineering physics, they will understand that there is a potential well diagram typically in a hydrogen atom problem. In this case, we refer to this as a triangular well. So, something like this we refer to, and then there will be fixed doping concentration and fixed quantized levels to explain to you. Now, the conduction band edge near the abrupt junction interface, you can understand this is an abrupt junction interface, right, it is an abrupt junction interface, and we say that the approximation of the triangular well is something like this, that at z greater than 0 it is something like rising function, but then you have a Vz is maximum infinity. So, this is infinity, at x equals to at z less than 0 it is infinite, this is infinite. So, it is always, the electrons are always confined in this small dimension device. Now, if you saw, so this is what I was talking about, right, you see, just look at this particular point, it is this confinement is somewhere here, right, and you can see here the confinement is so strong that there will be discrete energy levels here, and if you solve the Schrodinger wave equation, I will not go to details of that, not required for this course, but if you solve it, you will get discrete energy levels which can be formulated in case of a triangular wave function using this 2-dimensional electron gas. Now, of course, the current parallel to the interface, not the perpendicular to interface, will be a function of electron energy and electron mobility. So, it will depend upon the concentration of electrons and obviously on the mobility of the charge carriers. Now, since gallium arsenide can be lightly doped or is near intrinsic, the 2-dimensional electron gas which is there will have very low impurity scattering, and they will be minimized to the drastic minimum, and therefore, the mobility of the charge carriers will be much larger, and as a result you will have a larger current as compared to a standard silicon diode, right. So, the reason here is that since the doping concentration is very low on the gallium arsenide side, impurity scatterings are minimized, mobilities are very high, the currents are also very high in the direction parallel to the system, right. Now, if I do a graded aluminum gallium arsenide junction, then the right hand side shows you the conduction band edge of a gradient heterostructure, right. Here also the same thing happens, but since it is graded, it is not abrupt, the energy levels are not very well confined, right. In this case, the mobility of the charge carriers is slightly lower as compared to the previous case, right, for the reasons that it is a graded junction. The value of the electron mobility is much increased in this case. Now, in case of homojunction, whenever you add the two charges together, you will always have a thermal equilibrium being set up, right. And the potential difference which you see, which exists across the two space charge, is nothing but the built-in potentials which we have already referred to, and the built-in potential is nothing but the sum of the potential difference across the space charge region. So, whenever you cross a junction, you see a space charge, the space charge will generate a potential barrier, add the potential barriers, and that gives you basically the potential difference between the homojunction in case of a homojunction, right. The same diagram I have replicated it for a heterojunction in case of a thermal equilibrium. Let us not go into details of this, only last equation is very important, where you need to see the value of your Q times VBI. Q times VBI is your built-in energy, right, and that is equal to change in your valence band edge between when you add the two together, and it also depends upon the value of your PP0 and PN0 are the whole concentration in P type and N type materials respectively, and capital NVM and NVP are the effective density of states in N type and P type material. So, when you multiply that to you get the total amount of charge carriers available, and KT ln of that difference will give you the value of your built-in potential. So, you see, if you quite interestingly, this term is exactly the same as we do in homojunction. We have added a term here delta EV, which primarily is because of the abruptness of the junction which you see in the case of a homojunction. And in terms of conduction band shift, if you see, it will be minus delta EC which you will see, and that will give you the built-in potential value, right. I will end this topic with small example here, a numerical example, and you can have a look into it, and you can do it yourself and have a look into it. What we found out is that if you have an N type germanium with P type gallium arsenide heterostructure, and if you apply the electron affinity rule saying that the electron affinity will not change as you move, and this expression is valid, then we get that for all these values of P type and N type material, I get my V built in to be approximately equals to 1 volt. Now, however, and this is quite interesting, and you can actually look into it in much more detail. The barrier height for electrons and holes are different in case of a heterojunction, whereas it is same for a homojunction, right. The non-symmetricity does not occur in case of homojunction. Only for heterojunctions you will see that electrons barrier height is not equals to that of valence band of barrier heights for the holes, and the reason is the very fact that you are using a straddling type material, you will always have this difference between the two. Now, with this, let me recapitulate what we had discussed till now. We looked into the basic idea of homojunction, how a homojunction worked. So, we looked into homojunction initially, right. Then we came to heterojunction and explained to you the discontinuity and how is discontinuity related to other factors. Then we went to homojunction and explained to you how it is an ohmic contact and a Schottky contact, and then in heterojunction we applied the electron affinity rule and showed to you that if I take a straddling type material, I will get a discontinuity, and there will be a discontinuity edge where the two materials meet. That will also originate to get a 2D electron gas, 2D EG or 2D electron gas we refer to. And if you are interested, you can look at HEMT, maybe we will also come back to this at later courses. So, with this, let me stop at this particular point. Thank you.